Right. Now let's talk a little bit about power plants themselves. How do they look like? Beside the TS diagram and the sketches, how do they look like and what is the practical problems or feature they have? So let's start with the coal power plants. Of course, they will result in a lot of carbon dioxide that will be released, right? And that's why they are not that popular, but they are still being used. However, is it like completely out of the picture and no one ever will use coal in the future? There is so the problem with coal is the CO2, right? All this is gonna burn and make CO2, a lot of CO2. But there's something called clean coal technology, which is a way to reduce the amount of CO2 that is coming out and figure out a way to, there's a lot of research on how we can take the CO2 from the atmosphere and actually end up storing it. Okay, so in the US in particular, we have a lot of coal. This is a chart or the map of where the coals are. And if you read the history book, you'll find out that the pilgrims, when they came to the US, they were super excited about the coal that we have because it was so close. That means that it's so cheap to dig it out. You don't have to go very deep inside to pick it up. So we have a lot of coal, and so it will not disappear from our life. Okay, here is a chart of where coals are does exist in the US. And coal burners is a little bit complicated than natural gas burners. Natural gas burner, you just have to make sure that they mix the fuel efficiently with the air so that you have good combustion, you don't generate NOx, you don't generate hydrocarbon. Well, coal, because it's particle, it's a little bit more complicated, right? You need to break it, or basically, as you can see over here, you need to turn it into tiny particles, and you need to heat it, right? And then the burner design also is a little bit more complicated, as you can see over here. And so the point behind all this is that you want to have very good combustion so that you don't form CO, alright? So let alone the fact that we're gonna generate CO2, that's already a take, right? It's assumed, but at least you are not gonna form CO or unburned hydrocarbon. And you can see the different design where they try to mix and rotate so that they can have a good mixing. So now what is with the clean coal technology? So here is some idea that people are doing in order to basically, you need all those cyclone separator need to get rid of the ashes, and you need to also take care of any sulfur. So that's why they have a lot of limestone in order to take care of all the bad things that actually could exist in the coal, right? So fluidized bed technology, where the particles are floating while you are combusting them, and any particle that get swept out and gonna make soot, you basically pull it back with the cyclone separator, and then you refeed it back again. Okay, and only the hot gas is allowed to go to the furnace, to the rest of the boiler, to make the water boil basically for us. Okay, so circulating fluidized bed, I just want you to know there are efforts in order to make coal burners cheaply, and in Germany they also do a lot of research on making clean coal. And here is what they do in order to get rid of any sulfur. So some coals are too dirty to burn in the USA. We don't burn them. We are banned from burning them, and we actually export them. Okay, what other countries do, that's another story with them. But we cannot burn a certain type of coal if it has too much sulfur in it. But here is how you can get rid of the sulfur, by basically using limestone. Okay. So that is the equations that will allow you to get rid of the sulfur. Oxy-fuel combustion. So if you burn in oxygen rather than burning in air, that make over here, that why would you do this? That allow you to be able to get CO2 easily out of the combustion products, right? If you have air, that's too much nitrogen, but if you have just oxygen, then theoretically speaking, you can just have CO2 in the product. Therefore, let's take that CO2 in the product and let's basically store it, right? And we are done. No CO2 out. And you can see how he's basically doing a combined cycle over here too, right? So the raw gases is being run to a combustion chamber, and that combustion chamber is using air to burn and a gas turbine, and the exhaust of the gas turbine, before throw it away, he send it into a steam power plant. Okay, and the steam power plant is being burned, is basically fired by that exhaust, and also a little bit the water over here is being preheated by the furnace of the coal. Okay, so those basically tell us that there are hope that the technology will be advanced to that it's cheaper or like really efficient to burn coal without impacting the environment too much. Okay, so the point is, again in this slide, is that rather than burning in air, you burn in oxygen, you reduce the volume of the, or you increase the mass fraction of CO2, because it's all just CO2, there's no nitrogen, and then it's very easy for you to get CO2 and store it, capture it, and store it later on. Okay, so fluidized bed coal gasification. You turn the coal into gas, and that gas is cheaper, is cleaner to burn, right? So no soot particle will leave. Now, the reason why coal is losing the competition to natural gas is because natural gas is cheaper. So all that shale gas, formation that we have in the US, and all the fracking technology that they developed, make it super cheap to burn natural gas. And that's why a lot of power plant that's used to burn coal, they switch their burners and they start burning natural gas. And you just basically have pipeline coming from natural gas company into their boiler to basically fire the burners. Okay, and so here is the composition of natural gas. You can see that it's not just methane, although the majority is methane. So methane is what? CH4. So when we assume that the natural gas CH4, that's not a bad approximation. 95% is methane, a little bit ethane, a little bit propane, and very small fraction of other stuff, including hydrogen, oxygen, carbon dioxide, right? But the majority is methane, CH4. So power plant, steam power plant, we saw that sketch before. This is how in real life would look like. It's not just one turbine, 4 turbines, or 3. So high pressure, intermediate pressure, and low pressure. And you can see how the high pressure and low pressure, high pressure and intermediate pressure, they are sitting back to back. Why they are doing this? So that they cancel the axial thrust. See those pairing, they would have, if you go this way and you leave that way, you will generate axial thrust on the turbine. And axial thrust pairing is basically not as efficient as pairing that does not carry axial thrust. So by putting them back to back like this, they will cancel each other a little bit. And the same for the low pressure turbine. You basically make it into 2 parts, and they are sitting again back to each other. Okay, and we talked about all those feed water heater before, and we said why we have so many of them, so that we can help the liquid water get heated before it go to the boiler. The boiler will be in this place, right? You see how the high pressure turbine, the exhaust from the high pressure, rather than going directly to the intermediate pressure, you go for reheat in the boiler, Again, this place would be the boiler, and he will be coming back into the intermediate pressure turbine. The most of new power plants are now built from the start up with combined cycle. Okay, and so now whether the gas turbine is running on nuclear reactor or is actually running just by a combustion chamber burning natural gas, that's different. Some of them are running just natural gas, like the power plant we have in Owasso. So those is combined cycle steam power plant, and the burner or the furnace of the or the boiler of the steam power plant is being run by the exhaust of a gas turbine. And so it will look like this. Here is the gas turbine cycle, and here is the steam power plant sitting under it. And so that power plant in Owasso will have efficiency of 60 something compared to 40 something for the Jinx power plant, which is just running on natural gas. Steam power plant running natural gas, no a combined cycle. Yes, they have two gas turbines, but those two gas turbines, they got them later, and they are not coupled to the steam power plant. They are just sitting next to it as a peaker. Okay, but the Owasso one, it's running all the time. The gas turbine is running all the time, firing the steam power plant all the time. Okay, and we said that the first time this idea of using the exhaust of a gas turbine to boil water, because the exhaust is just too much, too high to throw away, it's like throwing free money, that was done in Oklahoma. Right, so we should be proud that we brought this to the whole world. This idea was brought to the whole world from Oklahoma. Okay, so here is another sketch showing the Brayton cycle, the gas turbine cycle, sitting on top of a Rankine cycle. And here, if you notice this, he's basically saying that the steam cycle could be multiple steam power plant under it, sitting at different pressures. Okay, so here is the Jinx power plant, and you can see here is a car pickup truck, and you can see how high it is. So this is just pure natural gas steam power plant. That exhaust over here, that's their gas turbine sitting away at the back. Alright, and so they, rather than going like this, they are actually supercritical boiler, or they like to call it steam generator, supercritical steam generator. Why? Because the pressure is above the critical pressure, so they go from liquid to vapor without making bubbles. Okay, there is no boiling in it. So here is, I love that sketch. That sketch show you how does this furnace look like. The exhaust is the end, but before we hit the exhaust, what happened? So the air come in, cold air from the outside, depending on the day. So what today is, like it was 50 something in the morning. So the cold air come, and he get preheated by the exhaust leaving. So that stack, before you send to the outside, you send the air into a air preheater. I'll show you some sketches of it in a second. But the air get preheated before he get admitted to the boiler. Alright, so we before we send natural gas on it, we heat the air, because why would we burn the fuel in cold air? No point. So we get some of the energy and we send into the natural gas pipeline or the burner. He burn and he make those big hot flames. Those hot flames are sitting in one big furnace. You can see how high it is. And this furnace or that boiler is hanging from the top. So why they hang it from the top rather than letting it stand on its feet? Why it's being hanged from the top over here? Free quiz. Why? Because the boiler at cold start is this tall, but when it get heated it become this tall. Right? And they make the joke that one time while it's maintenance, one guy put his toolbox under it, And when they started, you remember the toolbox was basically there, and they told him you have to come in 6 months to pick it up, because it's stuck because the boiler now expanded basically. Okay, so his toolbox was stuck there for 6 months. So it's hanging from the top, and what is that furnace? It's a bunch of pipes. All those pipes are surrounding the flame. That's where the water basically boil. Okay, from liquid to vapor. There is a drum on the top, and that make the steam, and the steam go into the superheater. Okay, so the superheater see the flame, so it get heated by radiation. The fact that you see, just like when you are sitting on the campfire and you put your hand and you can feel the heat in your hand. I mean, you don't put your hand on top of the flame, that would be convection, but just you putting it next to the flame and you feel the heat, that's radiation. Okay, and people in working for Jones Inc. know that. They know all those, they do all this calculation to figure out exactly how much radiation is going to the different part of the boiler. So the flame heat the superheater by radiation. Okay, and so that's why the superheater is the first thing to see the flame. And then after that there is the reheater. That is the steam coming from the intermediate turbine and going back, coming from the high pressure turbine exhaust and going back to the intermediate turbine. Okay, and then after that, that's the economizer. What's the economizer? It's the first place that the water go into the boiler. Okay, the first place that will start making it at basically B saturation, and then he go into the drum, and that's when he start continuing the part. So what I am saying is, here is what the turbine, the pump will send the water to the, what did we call it, the boiler feed pump will send the water over here, and the economizer will take you to saturation HF, and then you would boil in those pipes, on those vertical pipes. So that's the drum, and the economizer was here. So this would be 0.1. Okay, and so he go into this drum and he go down into the pipes, and then he become vapor, and he leave here at 2. Okay, so once he leave over here, he need to do the superheating part, and that's when he go into the superheater. That will take him to 3. Okay, and from 3 he will go to the high pressure turbine, expand, and then come back again, say at 4 for reheat, and leave at 5. So that would be this place where the steam will come over here at 4 and leave at 5. Okay, he come from the exit of the high pressure turbine, and he leave to go to the inlet of the intermediate pressure turbine. Okay, so the superheater, the preheater, the economizer, and the tube wall, basically it's a wall consisting of all those walls. Those are the sections that are being shown in this sketch. Okay, ouch. So that's what you are seeing over here: superheater, the reheater, the economizer. Okay, of course we need to help the economizer as much as we can by doing what? We help the economizer by doing, rather than giving the water to the economizer at say 0.0 over here, you wish 0.0 was over there, so his job is easier. So How do you go from here to here? This is TS diagram, of course. So how do you do this part? You do this part by the feed water heaters, the one that we pull from here and the one that we pull from here. All those feed water heater take the water from the exit of the pump to the inlet of the economizer. Okay, very good. So he's saying then you, after that, the economizer, use it to preheat the air coming in, but don't cool it too much. Why? To avoid condensation. Remember, we calculated the lower the temperature in the stack, that will make the water condensate. You don't want the water to condense inside your chimney. You rather want it to condense outside. Okay, very good. Also, that preheating is very useful. We said that, but it's also necessary for coal furnace, because you are not gonna burn coal in cold air. So you have to do it for coal furnaces. And here is another sketch of how does this higher drum and low drum, high drum and low drum look like. So you get the water from the economizer, the water going to the pipe to the lower drum by gravity, and basically all this heat, seeing the flame, make the water boil in the pipes, making bubbles. You take the steam out into the superheater. Okay, so this would be the place where you would boil into bubbles. But if you are running on a supercritical pump, sorry, supercritical boiler, you will just have no drum. You will just have water coming in, turning into vapor, leave to the superheater. So supercritical steam, it's they call it one through steam generator. Water in, vapor out. But here the water kind of circulate before it basically make it all bubbles. And here is a sketch of the drum, the steam drum. So what is the steam drum? It's a place where vapor leave and water go down. So we need to make sure that no water droplet get carried out. And why would water droplet be carried out? Because they are tiny. So they are easily can float with the air, right? In the right velocity, right? The drag will take care of it and carry it out. You will see this in experimental fluid, right? 4273. So how do we make sure no droplets leave? All those screens that they have different design, different pattern for how we can make sure no droplets is basically carried up. And this is the air preheater. So that air preheater is just one big disc that is rotating, and he's rotating between two streams. The chimney stream going up and the cold air that's basically being heated. And while he's being rotated like this, he's kind of like get roasted in the hot stream, and then that hot part get back again to the cold air. Okay, and this idea is not just for power plant. They use the same idea in big HVAC machines. So in big HVAC machines, before they throw the exhaust of the air from the building, and they have to throw the exhaust, especially in hospital, for example, you need to always throw the air and bring fresh air. So that air that they are throwing out could be like cold air in the middle of the summer. You're like, wow, I'm gonna throw all that cold air, that's a waste, right? Or it could be hot air in the middle of the winter, and like, why would I throw that very hot air? But you have to, because of the circulation. Otherwise the place will be stuffed and like people will not be able to breathe. So you do this wheel kind of between the stuff that you're throwing away and the cold air in the winter, or the hot air in the summer that's coming fresh. You make that heat transfer to transfer the heat. And obviously this has to rotate slowly so that he have a chance, the plates or the mesh have a chance to get soaked in the heat, right? So it's running at 3 RPM, for example. Of course, one of you could be looking down to this and like, this is horrible because you get some carried over. Yes, you will. Some of the hot gases that's leaving the stack will end up into the fresh air that's coming in. But that is okay, because in actual boiler, part of the control is to send some of the exhaust into the furnace again, right? We do this in car too. We do circulation sometimes to control the combustion quality. So I mean, don't worry too much about it in the power plant uh, context. It's okay to circulate some of the exhaust back in, right?